Okay, so continuing with exponential functions, what we're going to talk about today is solving exponential equations. And what that is going to, well, let's see here, today's goals. We want to be able to solve exponential equations in one variable and then solve exponential inequalities with one variable. And we're just going to touch on the inequalities, but understanding that the premise is still the same. What do we need to know? We need to make sure that we understand what an exponential equation is, and then compound interest and exponential inequality. Exponential equation, the independent variable is an exponent. So what we've seen here, so the property of equality for exponential equations, it's telling me, just focus here on this, is b to the x power is equal to b to the y power if and only if x and y are equal. So thinking about that with a number, if I had 7 to the first power equals 7 to some number, in order for those to be equality, I think many people would say, well, I guess x is 1, right? 7 to the first power is 7. Well, what would this be? This would be 7 to the first power, so x has got to be equal to 1. And that is the basics of being able to do an exponential equation. We have like bases, and then we just make the exponents equal to each other, which would be 1 is equal to x. So understanding that by virtue of the equality sign, if my bases are the same, the two things that must also be the same would be the exponents. Now, a special type of exponential function would be my compound interest. Compound interest is paid on the principal of an investment in any previously earned interest. Now, here is your compound interest formula. It is also on your state reference sheet, but just thinking about what does this mean, the compound interest formula A, this is how much we have. Okay, what was my value, the account value, then how much did I initially invest, times 1 plus the rate, and then the number of times that it compounds in a year, raised to the exponent of the number of times it compounds in the year times time. Time being how many years. For many of the equations that we do, the end is just going to be non-existent because it's just going to be once a year. But as long as we understand that that can change. So we'll do some examples. So here, how to solve an exponential equation. Well, I need to have like bases, okay? And so what we have here is we have 4, and an exponent of 5x plus 1 equals 64 to the 7th power. Okay, so what do we need to have like bases. So if I have a 4 here, I need to try and get a 4 in my other base. So what we find out is 64 to the 7th power is actually 4 cubed, right, is 64 raised to the 7th power. To simplify this more, now I know one of my properties, when I have a power raised to a power, we multiply them. So this would be 4 to the 7, 4 to the 3 times 7, or 4 to the 21st power. Now, so that's what we're doing here. We end up getting to this 4 like base, 4 like base. Bases are the same. So if I have 4 raised to some exponent, then it should be equal to the other 4 and its exponent. So in that case, I know that my exponents are equal based on the equality property there up top. So I simply take them and I make 5x plus 1 equal to 21, and I solve. Subtract 1 from both sides, 5x equals 20, divide by 5, and x is equal to 4. X equals 4 is the number that allows that statement to be true. Okay. So again, in order to continue or to begin solving an exponential equation, you have to have like bases. 4 and 64 are not like bases. We had to come up with something. You could have done 2. You could have said, we could have gone to 2 because 4 is technically, I'm sorry, 4 is the same thing as 2 squared, and we could have tried to find 2 as like bases, but we didn't need to go that small. Okay, it was just an option. Here, this is one of our problems from today's assignment. In order to solve for A, we have to have like bases. So you may want to stop the video, take a second and try to solve this and see what happens based on the information that we know. But if not, hey, I'm going to go ahead and solve it now. So 3 is the smallest base that I have. So can I find is 3, are there some multiples of 3 that equals 81? And yes, 3 to the 4th power is equal to 81. So I can replace 81 with 3 to the 4th power. And then I still have my exponent, 3 to the 3a plus 1. So I need to do some distributive property here, because this is, I'm going to write all the steps in here. This is 3 to the 4 times a plus 2 is equal to 3 to the 3a plus 1. Now you have like bases now. You can go ahead and start your exponential equation here, and because we have bases are the same, so my exponents must equal. So I have 4 times a plus 2 is equal to 3a plus 1. Using the distributive property, 4a plus 8 is equal to 3a plus 1. Subtracting 3a from both sides, because I'm trying to combine like terms, I have a plus 8 is equal to 1. Subtracting 8, and a is equal to negative 7. So if a is negative 7, then those two terms, then we maintain the equality there. So a has to be equal to 7. Just another example for us to look at. And then here is another example that they've given us, and what I've done is I've sort of tried to put some stuff over here in the margins. So 1 over a to the first is the same thing as a to the negative 1 over 1. So remember, that's how we change the sign of our exponent, is we put it over the radical, or I'm sorry, not the radical, the fraction bar. So here the same thing as 1 over a to the negative 1 would be the same thing as a to the first over 1. So just keeping that kind of thing in mind. Now, and before I tackle this problem, I'll look over here and say, okay, what is this? I know that this 2 to the negative 1 is the same thing as, and I'll just do this, is the same thing as 1 over 2 to the first. Okay, that's how we switch those, the signs of my exponents. So if that's the case, then I know that 1/2 is actually 2 to the negative first power. So then I can turn around and say that, well, 16 is 2 to the 4th power. So that's what they've done here, is they said, okay, well, 1/2 is technically 2 to the negative 1. Then we have 2 to the 4th power. So we have, at this point in time, we have negative 1 times 4x minus 16 is equal to 4 times 2x minus 5. Okay, that's what my exponents look like. Because we could have said right here that we have a base. Our base is 2. Then we have an exponent raised to an exponent. So end up, when they use the distributive property, distributing negative 1, we get negative 4, and then negative 1 times negative 16 is positive 16, equals 4 times 2x is 8x, 4 times negative 5 is negative 20. So your exponents, now that we have like bases, 2, would be negative 4x plus 16 is equal to 8x minus 20. Subtracting 8x from both sides, this becomes 0. Then I have negative 12x plus 16 is equal to negative 20. Then we need to move our numbers over to the other side. And then negative 12x equals negative 36, divide by negative 12, and then x is equal to 3. If x is 3, then these two terms are equal. So now here, again, understanding that what is going on with this 1/3. You can give this attempt to solve this and then check the video, but I'm going to go ahead and solve it now. I know that according to this, okay, this is the same thing. I got 1 over 3 to the first, which would be equal to 3 to the negative first. So this can be rewritten as 3 to the negative 1 times m is equal to, because that's my exponent, right? Think about it. This is 3 to the third times m plus 2. So I have like bases. So I have negative 1 times m is equal to 3 times m plus 2. And that's what I take my exponents and make them equal and solve. Again, this is negative m, right? Negative times m is going to be equal to 3m plus 6, because we had to use the distributive property. Subtracting, I'm just going to subtract 3m from both sides, because that way my number over there stays by itself. And then divide by the coefficient. And then m is going to be equal to negative 3/2. If m is negative 3/2, then we have a correct statement. So just looking at different ways to do this. The goal, though, is to get like bases, and then we move from there. Okay. Here, talking about solving by graphing. Since it began in 1966, the extremely high viewership of the Super Bowl has led companies to pay millions of dollars, right? Millions of dollars to advertise for 30 seconds. The average cost of a 30-second advertisement during the Super Bowl can be approximately modeled by the exponential function, where the initial cost is $58,000 and the average cost increase is 9.9% each Super Bowl. So write an exponential equation. So understanding my the cost is equal to, remember this compound interest formula, the cost is equal to what my initial investment times 1 plus the rate raised to the power of how many years, right? What is the time? They told me they said initial cost in 58,000, and then we're converting it to millions, because they said companies pay millions of dollars. So I think that must be what we're trying to calculate. The initial cost is 58,000, which is going to be 0.058 million. Then the rate of change, which is going to be 9.9%. Remember that you have to move your decimal point 2 places. So 1, 2. And then that's how we came up with my rate. So this should have been 0.058 times 1 plus 0.099, and then raised to the x power. So when they combined those, it became to 1.099. So that's how they came up with that. Now, when we want to estimate what is it going to be, so this is my equation. What is it going to be the average cost at first surpassed? When will it first go over $1 million? Now, this is where there's two different ways to do this, and I personally wouldn't do this method, but you can. 1 million, right? That's intended to be 1 million. You could make your y1 equal 1, your y2 into this equation, and then look and find out, when you calculate it, what is the intersection point. This is where it becomes 1 million. Okay? That is one option. That related function would have been, this is what they gave me. So remember, a related function, we would take, I have 1 equals 0.58 times 1.099 raised to the x power. You want it equal to 0, so I can subtract 1 from both sides. That's not 1. Subtract 1 from both sides. And then I have 0 is equal to 0.58, no, 0, 0.058 times 1.099 to the x power minus 1. And what I'm going to do is I'm going to put this in as my related function into the calculator. So then when I go to put it into the calculator, now if I look at the tables, I'm able to identify on my table that as I travel down from 23, 24, 25, get down here somewhere, 29, I've almost hit a 0, and then 30, I've almost hit a 0, and then what I can find out here is somewhere between 30 years and 31 years, I went from a negative to a positive, so I went to that next million. I went over a million, which would have been when I equaled 0, so I transitioned right here from 30 to 31 years, it went over $1 million. So just being able to identify what a related function is going to tell. So here in this method, we needed to find the intersection point with the related function. We would have to find the 0, find your 0. So looking now, according to their answer, it says that the solution to the x-coordinate of the point of intersection, which is about 30.16. Okay, so they calculated the intersection. And what I will show you is if we did that related function, that of course both answers will give us about 30.16. So on average, we would need in 31 years, the average cost of a 30-second ad first surpassed $1 million. 30 years, it wasn't quite, right, because it was 30.16. So we would have had to go to the 31-year point to find that $1 million. So just looking at different ways to evaluate that and understand that. And I'll just say, as we set this function up, it says cars, the moment you drive a car off a dealer's lot, it begins to depreciate or lose value. In 2017, the average price of a new pickup truck was $41,000. You can use an exponential function to model the value of the pickup truck over time. Okay, I know that the initial cost is $41,000. So $41,000, my initial cost. Says if the value of the pickup truck depreciates at 9%. Remember, your rate is 1 plus your rate. So we have 9%. 9% is the same thing as 0.09. So I have 1, depreciation means negative, so I have 1 minus 0.09%, so my rate should be, what is that, 0.91? Okay, so my rate then is going to be 0.91 times raised to the x power. And it says how many years will the new 2017 pickup truck be worth only, after how many years will a new 2017 pickup truck be worth only $20,000? Round to the nearest tenth. So if you put this into your tables, put that into your graphing calculator, look at your tables, it will tell you that. So as I put that into the graphing calculator and I look at it, after 5 years, it's worth $25,585, and it is depreciating over time, and then somewhere between 7 and 8 years, it's going to hit that $20,000 point. But it says round to the nearest tenth, so I can go farther in on on my calculator, and what you do is you hit the plus sign, and then the table will come up, and then you can change the table to 0.1, and that'll give you your 10% value. So here, when I changed the table to 0.1, it was an incremental 1, so I went to 0.1, and now it looks like instead of going from 7 to 8, I have 7.1, 7.2, 7.3, 7.4, and looking over here, after how many years will your new pickup truck be worth only $20,000? Well, at 7.6 years, it's worth $20,022, and then at 7.7 years, it is worth 19.834. And I have a feeling that if I were to round that, it's going to be somewhere along the lines of 7.6 years. It's going to be worth that $20,000. Narrowing it down even more, I made it to the 100th place of a decimal, and I can see that between 7.6 and 7.62, we have gone ahead and made that change. So it definitely would have rounded to 7.6. So just what year, how long did it take? And then here, using your compound interest, understanding what does my end value mean, and that is going to be how many times does something happen in a year? How many times is it compounded in a year? So when it talks in our word problem here, it says Luciana deposits $1,700 into a saving account that pays 1.8% annual interest compounded monthly. Okay, and then what will the balance be after 5 years? Compounded monthly, that's how many times in a year, every month. So since there's 12 months in a year, that is going to be, n is going to be equal to 12. Okay, so again, this formula is provided to you on your Tennessee reference sheet, but just keep that in mind. So what the value is going to be equal to the initial investment, the principal, times 1 plus the rate over n, and the n here is 12, the number of times per compounded annually, raised to the power of n times t, the time. So n again was 12 times the time, which was 5 years. So we just hear what they're missing is the principal, which is my initial investment, and then being able to put that into the calculator and make a determination. So you can put that straight into the calculator as a function or an equation, or you can put it into your tables. I will normally not do it all in one line like that on the graphic calculator, but I just figured I would show you that I put 1,700 times 1 plus 0.018. I didn't need to simplify that. The calculator is going to do it for me. Over 12, raised to the power of 12 times 5, and that gives me the value after 5 years, what Luciana's account will be. So that's what we're doing here. Over here, this is just breaking down what do these values mean. This is the output. What is the amount going to be worth? This is how much did I initially invest, or my principal. Then I have 1 plus my rate over the number of times that it is compounded annually, and then the number of times that it is compounded annually times time. Compounded annually, they could say quarterly, which would be 4 times a year. They could say daily, which would be 365. They could, and of course, monthly or weekly, which would be 52. It just depends on what they're specifying for the value of n. And then when we look at this last example that we're going to do, and she deposits $500 into a checking account that pays 0.9% annual interest compounded twice a month. What will her account balance be in 25 years? Okay, twice a month, which is 24 times a year. So you have an initial investment. A equals the initial investment times 1 plus my rate. It's going to be 0.09. No, move it twice, right? 0.0. 9 over, we said twice a month, so that would be 24 times a year. and that would be 24 times the number of years would be 25 years. And that is what we would solve to come up with an answer. Okay. So there you go. Looking at that, that's how we are processing through these exponential functions and exponential equations. We'll do a lot of this practice, but just making sure that we know what these all stand for. Every year I get it from students asking me, what is this? It's the principal. What is the principal? It's my initial investment. So making sure we understand those vocabulary words so we can actually process through our equations and understand what they're asking us.